Why don't we begin here? So welcome to Stat 950, Bootstrap Methods and Their Application. For those of you who may not know me, my name is Chris Biller. I'm a professor in the Department of Statistics. Let's begin by taking a look at the syllabus here. Okay. Overachievers. Okay, so let's get my copy of the syllabus. So, Stat 950. This is a PhD level course in our department. For those of you who have maybe taken me for another course like Stat 875 or Stat 870, there are higher expectations with this kind of a course than with with a previous course that you may have had me with. Now, I know there's some master's students in here, and you're welcome to take this course, but you got to realize that there are higher expectations with this. That this is a PhD level course. I have had master's students do very well, though, in this course, just so not totally frightening. I do think that this course is difficult. At least when I had a corresponding course when I was a student, I found it difficult. I don't know. I think some of my students have found it difficult. I don't know what you've heard through the grapevine, if this is difficult or not. I wouldn't be surprised if they said it's difficult, but I'll let you judge that on your own. You do need to put the time into this course and to fully understand what we're doing here. It's very easy, especially with the notation. It gets very easy to misunderstand what we're talking about. And so you do need to put more time into it than you would maybe an 800 level course. Let me actually go to the syllabus then. So, I guess, again, my name is Chris Biller. Please call me Chris. Don't call me Dr. Builder. Call me Chris, not Dr. Builder. My office is in 342D, up in the north wing of the building. Here's an old map of what East Campus looked like a few years ago, when it was Hardin Center, not Hardin Hall. And my office is right there in the northeast corner, if you're not familiar with it. My office hours are 12:45 to 1:45 on Tuesdays and Thursdays. I teach in Keim Hall 11 to 12:15, so it's going to take me a few minutes to get back to my office. I anticipate I'll be back by 12:45, but you never know. So if I'm not there right at 12:45, please be patient. Of course, you can always make an appointment with me as well. The web portal to all my course websites is chrisbiller.com. Basically what chrisbiller.com is just an easy way to forward you to the actual physical location on the UNL web servers. And this is what it looks like. And if you come down here to Stat 950, you get to the actual course website. You can do chrisbiller.com/boot to get to it, or actually type in that long address there. Note that we will not be using Blackboard for this course, except for I will post final grades there at the end of the course. My email address is builder@unl.edu. And as for textbooks, this is what it should look like. You got this, you got the right book. I think this is a fairly cheap book, at least comparatively to others. There. How much did any of you pay for it? Okay, good. This is by far I think the number one Bootstrap book out there. There are other ones, but I think this one's the best, even though it is showing its age, and you can see it's kind of showing its age. In terms of mine's not looking in good shape. The book itself, if you have your book, please take it out. It would be helpful to bring your book to class every day. All good students bring their books to class every day. Anyway, I guess I will just tell you then why it's a good book. The book it was written in 1997, and you will note that the exercises in the book are divided into two different kinds. One's called problems, and one's called practicals. Problems are often based upon theory-based exercises. Prove something, for example. The practicals are based upon doing stuff on the computer. Specifically, what made this book revolutionary, actually, at the time when it was written, is that it actually gives you, and you can kind of see this, it actually gives you, on the right-hand side there, actually gives you, R code. Now, at the time, R didn't exist. Well, people didn't really know about it. It was in very early beta formats. But at the time, R didn't exist, so this is actually S+ code, if you've heard of that software package. And basically, R uses pretty much the same syntax as S+. So you can basically run all this code in R. Okay? So that's a really nice aspect to have. I mean, nowadays, this is common to have something like this. If you want to write a new book, just put the statistical method and attach the word R to it, and you got a new book. I speak from experience. Anyway, also with this book, too, in Chapter 11 of the book, structured section 11.1, 11.2, 11.3, and so on, but each of those sections then gives you additional help with how to use the computer, in terms of R for us, how to use the computer to do the stuff in the corresponding chapters. So section 11.2 gives you some extra help for chapter 2. Section 11.3 gives you some extra help for chapter 3. All the code that's in chapter 11 and in the practicals that's listed here in the book is available on the book's website. And there is a link to it on my course website. Okay? So you shouldn't have to actually type in any of their code. Is everyone clear on that? Okay. But one disadvantage of using this book, and I'm going to mention this more than once today, more than once this semester, is that there's an expectation that you've had a course in asymptotics. In other words, be able to prove that as n goes to infinity, the distribution of some statistic is something. How many of you had a course on asymptotics? Maybe I should phrase it this way. How many of you not had a course on asymptotics? Okay. That makes this book more difficult to read then, obviously. Ideally, the best time to take a course on the Bootstrap is as your very last PhD course. Of course, that's kind of difficult to do because you got other stuff you got to take. You can't always wait till the last course to take this. And the reason why I say that is because, it would be nice if you had a course on asymptotics. Asymptotics is not a prerequisite for the course, and I'll help you through some of that stuff. Pretty much you need to get to a point where you can read it, understand what convergence and distribution means. You have a general idea of how they're approaching a particular problem, why they say this is an approximate distribution for a statistic. But also, the reason why I say that it's best to take this course at the end of your PhD career is because the Bootstrap is used in so many different areas. For example, the Bootstrap's used in survival analysis. And in fact, there's a section on the Bootstrap and survival analysis in this book. So if you haven't had survival analysis yet, it's hard to understand what they're talking about, how the Bootstrap is going to be used for it. The Bootstrap is used in a number of different areas. Nonlinear models. If you haven't had a course on nonlinear models, well, sorry, the section in this book is going to be difficult to understand. So, because of that, the approach that I take when I teach this kind of course is to teach you the basics of what the Bootstrap allows you to do in the context of what I expect for all of you to have experience with. Basic hypothesis tests, basic confidence intervals, regression analysis. That's what I focus on in this class. Then, hopefully, you'll end up using the Bootstrap in your own research, and based upon that background, you'll be able to say, okay, now I'm doing research and survival analysis. Now, based upon what I've learned previously for these more easier problems, I know how to extend it now to my own research problem. Okay? So that's how I approach this kind of a course. Now, there are other books out there. Probably the number 2 book is Efron and Tibshirani's An Introduction to the Bootstrap. This is the first book that came out. It's also the easier read than this particular book. When I took a course like this, I also read Efron and Tibshirani at the same time. Anybody know who Efron is, by chance? That's Bradley Efron. He's actually, you could say, to some respect, the inventor of the Bootstrap. Okay? So he wrote the first book on it, and then a number of other books came along after it. Unfortunately, Efron and Tibshirani doesn't go into as much stuff as Davison and Hinckley's book, so that's why I use Davison and Hinckley's book. There are other books out there, such as Peter Hall's book, The Bootstrap and Edgeworth Expansion. Basically, that really gets into all the theory behind the bootstrap and is just focused on that. It really gets into the asymptotics part. The Edgeworth expansion, as you will see a little bit later on in the course, basically what that is a way to asymptotically approximate the distribution of how should I say, get an approximation for an actual distribution itself. Without going into all the details. Well, you'll see more on that later. Lunenburg's book is more written at a lot lower level, maybe introductory master's level. But still, that can be then helpful to be able to understand it at the level that we're going to approach it. Prerequisites. You need to be really, really, really good at Stat 882 and 883. Because we're going to rely on that stuff, that kind of a background throughout this course. Very important that you did well in that course. So not just take it, but did well. Also, you need to have some background in regression analysis, preferably Stat 970, but 870 will work too. We're not going to really get into much regression stuff until Chapter 6. That's more towards the end of the course, so stay tuned for that. Also, you need to have some prior experience with R software. I am not going to do an introduction to R here. You need to have had experience with it before coming to this class. If you haven't had experience with R, you probably shouldn't take this course. You can talk to me more later if you want to. When I say in terms of your experience level, well, if you've taken a course with me, some other course, we've talked about R, that will be enough. If you haven't taken a course with me before, what you need to have done is, let's say, at least use R throughout in another entire course, more so than, let's say, your professor giving you some code and you ran 1 or 2 R programs. You really need to have some R experience before approaching this. Grades. Test 1, 25% of your grade. Test 2 will be 25% of your grade. Final exam, comprehensive, will be 20% of your grade. And lastly, there will be a number of projects and quizzes throughout the semester that will be all combined to be 30% of your grade. Everything's scaled to that. So what I mean by that is, let's say you did great on Test 1, Test 2, and final exam. All of them you got 100%. Let's say you didn't do any projects or quizzes. Well, you get 0% for that, so overall your grade would be 70%. Okay, so that's how that would work. Grades. Just common grading scale there, where plus and minus letter grades are assigned 2.5% from the cutoff points. Now, I will be grading everything electronically. You will not hand in anything in terms of projects to me on paper. Because of that, you need to turn in all your projects electronically to me in Word documents. If it's a PDF, we can discuss what we can do about that if you don't want to use Word. But some of these projects may be kind of long, and there's going to be a lot of mathematical symbols. There's going to be a lot of Greek letters floating around, and you need to do everything in a professional manner. So, for example, I don't want to see, let's say, the Greek letter mu is used for something that we're doing. I don't want you to simply type mu. You need to actually use the Greek symbol mu. So, if your project's not organized in a nice manner, I will turn it back to you, and you'll need to redo it. But with completing projects, you are welcome to work in groups to do that. I guess I'm a strong proponent of group work, that you can learn from your fellow students just like you can learn from me, and so I encourage you to work in groups on the projects. But when you do that, please remember that everyone needs to fully participate on the projects itself. So, statistical software, as I've kind of alluded to, we will be using R for everything in this class. No other software package will be used. You need to complete everything with R. You can download it. Hopefully you know this by now. There's the Windows-based version. It's also available in Unix and in Apple versions as well. Class recordings. I will record all classes this semester. As you maybe have seen already, I have a little camera set up right there that I am recording with. I'm using a package called Cam Relay, and I'm using a different aspect to it than what I had used before. They recently upgraded Cam Relay so that you can actually get video in addition to audio and what's on my computer screen. And so I'm hoping that it works. I did not know that they had upgraded Cam Relay on campus until about 2 hours before class. So I have not had a chance to test it out. But it's a very convenient tool, and just to give you a little bit of idea of how it works. So what's happening right now is that everything's being recorded via that camera right there. Both the audio comes from that camera and also obviously the video. And everything's being recorded on my hard drive right now. Then after class, I'll get in my car, drive home. After I say hi to my kids, I will plug my computer in and allow it to upload the corresponding file to a server that's located on campus that the Information Technology Group has on city campus. That uploading, at least with the previous version of Cam Relay, would take about an hour to 2 hours. I'm afraid that given the video portion now, I'm afraid how long it's going to take. I mean, I wouldn't be surprised if it's a 2 gigabyte, 3 gigabyte file. We will see. Then the server has to do some post-processing to it to make it a version that all of you can view as a video. So, at least with the past version of Cam Relay, I would get email about 9, 10 o'clock at night when I would teach a class about this time saying, okay, the video is ready. Once I get that email, then I post a link to the video on my course website so that you can view. So, be expecting, hopefully, if everything works out right, maybe by 10 o'clock the video will be available for you guys to view. Now, with this video, use it for, maybe if you didn't understand something the first time in class, you want to relive your classroom experience and maybe hopefully understand it better by viewing the video. That's what you need to use this video for. Also, there will be a few times, well, hopefully not a few times, but there may be a few times during the semester when you can't attend class. Well, here's your backup. But please don't take advantage of the fact that these videos are out there and not come to class. The final exam, it's scheduled for 1 to 3 p.m. on Tuesday, December 11th. This is the date of the final exam. Please don't ask me to take it earlier or later. So expectations of students, as I've kind of said before, this can be a tough class. It's a tough book. But please make an attempt to read the corresponding sections of the book as we go through them in class. I know when I was a student taking this course, I often would read an example and think, okay, I kind of have a general understanding of what's going on. And then I read that example again, it's like, oh, I missed a lot. There's a lot buried into some of these examples. So, please take the time to read the book as we go along the corresponding sections in the course. Also, you're responsible for, of course, all the stuff that I have in my lecture notes. I wouldn't put in my lecture notes if it wasn't important. And I do recommend rerunning all of my R programs that we do here, that we talk about in class. Run them line by line so that you know, okay, this is what this line does, this is what this line does, versus run the whole program and say, okay, yeah, that makes sense. No, you need to understand what's going on with R. The Bootstrap wouldn't actually be used if we didn't have computer software. And so there's a heavy emphasis in this class on how to actually use computer software to do it. Okay, let's see if there was anything else. Okay, are there any questions?
Will we have access to the R code on our websites during the exams?
Yes, yeah, and thank you for bringing that up. All the exams that we will be taking are computer-based, so you will be using the computers that are in here to take the exams. Now, I don't want you to have to memorize code. So what I will do on the exams is make available the R code that's on my website for you to use. Any other questions? Okay. Let's briefly talk about the course website that I've set up here. On the left-hand side, you see it's just basically like a little menu bar. It has pretty self-explanatory. The labels are pretty self-explanatory. What's contained by clicking on these various things in the menu. If we take a look at the schedule web page, though, I want to point out a few web pages here to make sure it's clear what's available. Schedule web page gives a tentative listing of what I expect we will be able to cover and when we will be able to cover it. Let me emphasize that this is tentative. This is based upon teaching this course. I think this is the 4th time I've taught this course, so 3 other times. And what you'll see here are tentative dates for when I expect the tests will be. These dates are likely to change depending upon where we are in the semester. So it could actually be, this test could actually be on September 20th, or it could be September 27th. Just gives you a general idea of when I expect it to be. Right now, I'm hoping test number 1 covers basically only Chapter 2 and the little intro that we do in Chapter 1. Chapter 2 is really the big chapter of our book. So you can see where approximate date for test number 2 is. And you'll notice there are, let's take a look at today. We're doing an introduction right now, and then we're going to get into Chapter 1. Notice there's a hyperlink there. That's because you can download the corresponding lecture notes. Now today, since this is the first day of class, and maybe some of you weren't looking at my website prior to our class, you might not have already done this already. Maybe some of you have. You can download, I will pass out the Chapter 1 lecture notes. But after today, I will never pass out notes in class. You will be responsible to come here to the website and actually download the notes yourselves. I recommend printing off the lecture notes and bring them to class. You can take notes on them, or you can just simply bring your laptop, or maybe you can use the computers here and take notes that way as well. We will have a day number 1 quiz, which we will briefly talk about. We talk about shortly, and also we'll talk about this listserv shortly as well. Do note that this day number 1 quiz, in case I forget to mention, is due Friday at 5 p.m. and you will need to email it to me. Okay, so that's the schedule web page. Let's talk about the chat room. Nights before exams, I will be available in the chat room for virtual office hours. So if you have any last-minute questions, please feel free to stop by. The chat room itself, I use Adobe Connect Professional for the chat room, and this is basically just a web conferencing software. And if I click on here, I can open it up, and if you use your my.unl or your Blackboard or your LDAP login and password, you'll be able to log in. And so let me just do that. As you would expect with any kind of chat room, there is a place where you can type information, such as hello, and it will appear like that as well. So that's briefly what the chat room looks like. Homework. Homework in my classes contains additional problems for you to work on. Some of these are from the book, some of these are ones I've made up, some of them are from previous tests that I have given. These homework problems are not collected and they are not graded, but it is to your benefit to do the homework problems, because I will often, for future tests, actually take problems directly from the homework. You will note that with these homeworks, I also have partial solutions with them to help you out. I will not go over these homework problems in class unless you have questions about them. Let's see. So let's talk about the listserv here. So I think all of you have experienced with listservs before. This is what our listserv is. Looks like in our class. It just gives us a way for all of us to communicate as one group. And basically what you see here is what kind of looks like a message board archive, and in fact this listserv is very much like a message board. So if we click on July 2012, week 5, when I was updating my website, you'll see that I have posted a welcome message to all of you. Hopefully you've seen it. Maybe some of you haven't. And if I click on the welcome, we have this really short message just describing what is this listserv for in our class. Real briefly. You can post messages regarding questions on homework problems, projects, or other things relevant to the class. You can post them here. If you have a question regarding your grade or something that's more personal about yourself, like you're going to be absent from class, don't post those kinds of questions. Don't post those kinds of messages here. You know, most students in class don't care if you're not going to be able to make it to class a particular day. But questions where other students could potentially benefit from seeing the answer, like on a question about a project or a question about an upcoming test, post the message here. If you're ever in doubt what to do, just ask yourself, will other students benefit from seeing the message? If the answer is yes, post it here. If the answer is no, email me. But you can also use this listserv too to post messages to, hold on. If you want to communicate with other students as well. So, you know, maybe if you want to ask at the beginning of the semester, does anyone need another group member, you can post a message here. Or maybe you have a question about a homework problem, you can post it there as well, that where you want other students to reply. Now, how do you actually post the message to the listserv? Let me go back to the original page here. The first thing you need to do before you can actually post, though, you need to join the listserv, or subscribe to the listserv, you could say. And you can click on the join link. And this is already pre-filled in because I'm already a member. But I will not be pre-filled in for you. Just simply fill this out. You can go with all the defaults about how you subscribe to the listserv. And down here you'll have something that says join. You click on join, and now you're a member. Once you do that, then you can simply email this address whenever you want to post something to the listserv. Alternatively, what you can do is use the web interface to post a message. You can click on Post New Message. Up will pop up this little screen, and you can do something like this, test message. And I'll just say test message. And come down here, click on Send. And it's sent to the listserv. So if I come back here, you now see August 2012, week 3. Here's my message that I have posted. So you can use the web interface, or you can just simply email that address. Both will work. Do note that if you use the web interface, you actually have to go through some additional subscription steps, and I have given those steps in this listserv help file. So please note that. Let's see. Let's talk about R. So here are all the programs that we're going to be looking at during this semester. Again, during a test, you will have access to this. You will not have access to my lecture notes. It is a closed book exam, closed note exam, except for you can use my R programs. So anything that we do in R will be in those programs. Are there any questions about the website? Okay, let's talk about this day number 1 quiz. So again, it's due on Friday. So you can just download it from that address. I've already downloaded it. So let me bring up the file. Excuse me. There we go. So simply number 1 and number 2 is just to give you some experience with the course website. I want to make sure that you know how to use the chat room. I want to make sure you know how to use the listserv. So number 1, log on to the chat room, send a test message. Make sure that you include your name. Number 2, log on to the listserv and join the list based upon how I showed you earlier, and actually submit a message. Number 3, then what you often have in most classes at the beginning of the semester, tell me a little information about yourself. Please fill this in on this table. And number 4. Number 4 is a small problem where what I'm trying to do is evaluate your background in R. And if you can't get all the problems, that's okay. I will not grade based upon correctness. I will grade based upon that you made an attempt. Okay? So, part A. What program editor do you use for R programs? Part B. What I want you to do is simply type this code. You see this library boot? Does anyone know what that does? It uses the Bootstrap package. This is the main package that we will use throughout the course to do our bootstrapping. Now that package is actually based upon the code that was written for this book. Obviously, again, this book was written before R really was in existence or available to the general public. So what's happened is that the functions in this book have been adapted to R and now are in the boot package. And what I've done here is simply write a little function to calculate a correlation coefficient, Pearson correlation coefficient, that is. And what you're going to do is run the function with a particular data set called CD4. This is within inside the boot package. These are CD4 counts. You look at the help for CD4 to see exactly what information is in it. And you put the results into an object called say.it. And if you say say.it, you get the results back to you. I want you to simply run the code, show me you can run it, and show me what the result was. Then we get a little bit more complicated. Part C. In this call to this function, you'll notice that there was no specification of this W argument that you see here. Well, then what is W? I want to make sure that you understand how R works in terms of function calls. Part D. Suppose I wanted, let me back up. So this function, the way it's written right now, will only give you the Pearson correlation coefficient back. But suppose I want some additional information back. Let's say something that's in the object M1 that's in the function. How could you change the code so that M1 is also returned in addition to the correlation coefficient? So change the function, run it, include all that information in what you hand in, and put it right here.
So you want the actual code, not just a description?
Yeah, I want the actual code. Yeah, sorry if that wasn't clear. I want to see the actual code. I want to see it actually implemented. And also you might have to actually give some written response about, well, this is what I did. This is why I did it. Then, part E. I want to make sure that you can change some additional stuff in the function itself that will be useful in a diagnostic setting where you're trying to diagnose maybe problems that are occurring in a particular function that you have written yourself, and you're trying to figure out what's going on. And so what I've done here is say, I want you to rewrite the function so that certain elements are actually printed from inside the function itself. Not the very end of running the function, but print it in from within inside the function. So there's two, at least that I know of, there's two functions that in R that could be used that could actually do that. Part F evaluates if you have experience with Monte Carlo simulation. Hopefully you've seen Monte Carlo simulation in another class before. And I would assume one of the first places like Stat 883. Does that sound familiar? Okay. So I want you to do a little Monte Carlo simulation here with R. Simulate 1,000 samples of n equal 20 from a bivariate normal distribution with this mean vector, these variances, and this covariance. I'm not telling you what function. There's a function in R that will automatically do this for you. I'm not telling you which it is. I'm kind of evaluating here your ability to use, to search R help for how to come up with that. These are all kind of things that you're going to have to do in this class. So, copy and paste the R executed code into the document, and please remember to include a C number so I can reproduce your exact sample. And lastly, so you're going to get 1,000 samples, and you're going to get 1,000 correlations from those samples. Plot a histogram, and overlay the asymptotic normal distribution on it. The asymptotic normal distribution for Pearson correlation coefficient. I'm not going to tell you what that asymptotic distribution is. You could derive it, or you can maybe find it someplace else. Just let me know how you found it, okay? I don't care how you get it. Just let me know how you found it. I would hope that in our advanced probability course that we have here, Stat 980, I think it is, I would hope that you would actually go through the proof of the asymptotic normal distribution for the Pearson correlation. Has anybody taken 980 and you don't do it? That's too bad. Okay.
We kind of just
Okay.
Yeah.
I assume you've done the delta method. Okay. And you've done large sample distributions of moments. Does that sound familiar? Okay. You're going to learn some new stuff here in our class. Okay. And now, again, I don't want to worry about the asymptotics part. You know, I will. Asymptotics is not a prerequisite, and I will typically walk you through that kind of stuff. But in order to read the book, you're going to need to know, when someone throws up a convergence and distribution, what that means. What that means to you, not necessarily how to prove it, but what it means. And for those of you who are stat students going on for a PhD in statistics, understanding the asymptotics is very important. Pick up a copy of JASA, Journal of the American Statistical Association. Look at it. They're doing asymptotics all over the place. And if you don't have that asymptotics background, it's going to really hurt your ability to do research. So, okay. I think that's it then. So day number 1 quiz is due on Friday, 5 p.m. Again, so put all your answers in this document here for number 4 and also number 3 and email it to me by 5 p.m. on Friday. Again, I grade on this particular case, not necessarily on correctness, but on attempt. And try to limit the number the time that you spend on number 4 to, let's say, less than 3 hours. I don't want you to be teaching yourself a whole course on asymptotics so you can get part G there, where you spend hundreds of hours. I don't know if there's hundreds of hours before our class on Friday, but make an attempt. At least do a Google search, see if you can get it, and just tell me what you try to do. Okay. Are there any questions before we move on? Okay, next, I think, is Chapter 1. Great, I got a whole bunch of scratch paper that I can use now. Okay, so to give you a little bit of an idea of how I usually conduct classes, at the very beginning of class, what I'll do is I'll usually start off by taking a look at the schedule web page to see where we are in the semester, what's coming up, and give you some reminders about stuff that might be due. And then what I will say is, are there any questions? This is your cue to ask me questions about previous classes, about homework, about projects, about tests, whatever. So, are there any questions at this time before we go on to Chapter 1? Okay. Chapter 1. So let's just give you a brief background into what is the Bootstrap. Where did the name come from? It's one of the few, I think, things in statistics where we have an interesting name. And where does the Bootstrap fit in the whole statistical science? What is it used for? And so let's begin with here the big picture of what is statistics. So a diagram that I like to use in my introductory stat courses to show what we do in statistics. And to help explain this diagram here, what I'm going to do is go through an example. And let's say that we were interested in estimating the mean GPA of all UNL students. So, we have like population of size about 25,000. And let's say that we can't just simply go over to, we call it the registrar's office. I don't think it's called that here. The registration and records. Let's say we can't go over to registration and records and get that information. Where if we wanted to know the mean GPA of all students on campus, we would have to actually ask every single student, what is your GPA? Obviously, that might take a lot of time. So what will we do in statistics? First of all, we would define our population of interest. All students at UNL, all 25,000. So you can imagine, including yourself, all 25,000 students are floating around in this circle. And attached to each student, you have a GPA. We define a random variable. That's our characteristic of the population that's of interest to us, specifically the GPAs. So let's let Y be a random variable denoting our GPAs. And we're not just necessarily interested in every single person's GPA. While we need that to do what we want to do, what we're actually interested in is a summary of all those GPAs, a numerical summary, a parameter. In other words, the mean GPA. So let's let theta be our population mean. We're interested in theta. We really want to know what theta is. So one thing that we might do is maybe actually have a probability distribution then for all these GPAs that exist in the population. So all 25,000, you could come up with a probability distribution associated with all 25,000 students and their GPAs. That tell you, what's the probability that a GPA is greater than, let's say, 3.0 or less than 3.0. And so what that probability distribution does helps kind of summarize what it looks like. I'm kind of drawing a normal distribution for you, not necessarily because it's a normal distribution, but, we might have something that looks like this. Here's 0, here's 4. I don't know, I've always envisioned it to be more like this. Or, no, not like that. Never mind. Let me get my red pen out. I've always imagined it to be something like this, kind of a beta distribution, but scaled to be between 0 and 4 rather than 0 and 1. So maybe that's the distribution. So that's let's say our f of y. That's our probability density function. We could also have our cumulative density function, capital F of y, our CDF. Now, what you'll notice in this book is a shorthand notation. Rather than saying, let's see now. Now, I guess if we want to be general, often you use this kind of notation. Y is distributed, let's say, normal, 0, sigma squared, right? Well, if we want to be really general, we're going to use this notation. And we will often want to be really general. We'll say Y is distributed F. So the capital F comes from the CDF. we'll say y is distributed f to say, okay, y has some distribution out there, but maybe I don't necessarily know it. Well, it's going to be hard to get at all the elements in the population to actually know what the mean GPA is, to know the actual distribution of the GPAs as well. So what we do in the statistical sciences, we take a representative sample. So we actually go within inside the population. We take the sample out, and there's my sample. And the samples are represented by a smaller circle, so maybe a sample size 20, for example. So you can imagine 20 GPAs floating around in here. It's a smaller set of information, a lot easier to work with than in the population itself, since the population has 25,000 elements in it. And in this sample, let me say this first of all, we might want to take a simple random sample to actually obtain the sample, where every element has an equal probability of being chosen. So if we have 25,000 students, roughly every element might have 1 over 25,000 as its probability of being chosen. Now, if I simply sample this person, and go sample this person, and go sample that person, this person had a probability of 1 over 25,000. Since I already had that person, this person over here now has a probability of 1 over 24,999. So it's roughly about the same. But as long as you have a very large population, it's not going to matter. It's just about the same. Okay? So every element has an equal probability of being selected. This is actually going to play a very important role for us when we discuss the bootstrap and how we do the bootstrap, I should say. So maybe this is what our sample looks like. If we look at the corresponding random variables representing GPAs, we have a capital Y1, capital Y2 down to capital YN, if I had just a general sample size n. Then their corresponding actual observed values, like maybe 3.0, maybe like 3.2, are, of course, lowercase y's, using the same notation that you would expect in a mathematical statistics class. Now that I have the sample then, what I want to do is summarize the sample in a similar way to what you would summarize the population. And I summarize the sample with a statistic. That's where the name statistics comes from. So statistics is a numerical summary measure used to describe a sample characteristic. So how about we let T then be the sample mean? Capital T is our random variable. Lowercase t is the actual observed value. So we could say that capital T is an estimator of theta. Sample mean estimates the population. Lowercase t is an estimate of theta. It's actual numerical value. That's the symbol that we use to denote the numerical value. Again, this is that 882 stuff, actually. Now, this is where the statistical science comes in. So I have the sample here, and I want to say something about the population. I want to say some stuff about the population mean. So what I want to do is actually make judgments, decisions, inferences from the sample, what I got in the sample, back to what the population gives us. And I want to do it with a certain level of accuracy. How do I do that? Well, use hypothesis tests, confidence intervals, based upon what I've calculated in the sample. Okay. All this stuff that I've said so far should not be new to you. So, because of that, now I'm going to ask you a question. Hopefully none of you have actually looked at the answer that's underneath that black highlighted area right there. But here's the question. So, I might say I have a 95% confidence interval, or I might say I have a type 1 error rate of 5%. Where does this level of accuracy come from? What is actually driving us to be able to say, I have this level of accuracy?
The distribution of your estimate.
Yeah. So what do we call that distribution often? What's the name?
Sampling distribution.
Sampling distribution. I hope I didn't have the answer listed there or down below. I hope none of you were looking at that. Sorry, I paged up too high, perhaps. So let me move that out. So sampling distribution statistics. This might be the most important thing in the whole world of statistics. is to come up with the sampling distribution of a statistic. Because that's how you derive confidence intervals. That's how you derive hypothesis tests, so that you can say with a certain level of accuracy what's going on about the population. So what is then this true sampling distribution for our statistic? Remember, our statistic is T. What's its distribution? Is it normal? Yes or no? Asymptotically, it's normal, yes. But is it actually normal? No. If I have a finite population, in fact, T has a discrete distribution. Its distribution is based upon this. Suppose I have a capital N is my population size, 25,000. Let's say I'm taking samples of size, I'm taking a sample of size N, maybe 20 from it. Then there are capital N, choose small n, different possible samples that you could obtain. You can calculate T for every single one of those. Look at the probability of getting T equal 3.0, T of 3.1 maybe, T of 3.02. In terms of, look at the number of times, I should say, that you get, let's say, T equal 3.0, T of 3.1, T of 3.2. Take those number of times at frequency divided by the total number of possible samples, and there you go. There's the probability of getting that value of T. That's the actual sampling distribution. Anybody ever calculated a sampling distribution like that before? You have? Good. For class? Or just for fun?
I think it was for fun.
Okay, which class?
I don't remember now, but I got it. We did. It was small.
Okay. That might be you might do it in a non-parametric class. But let's say that your population is an infinite size. How many different possible samples are there? Infinite. So you're going to be able to actually calculate the sampling distribution of T? No. Unless you say something about the population distribution of Y. I'm sorry, the probability distribution of Y. If you say something about the probability distribution of Y, let's say I say Y is normal. Well, yeah, you could derive what the distribution of T is. It's normal. That's what you would have to do. So there are three ways that we can approximate then the sampling distribution for T. Again, let me remind you why this is important. If you want to do confidence intervals, if you want to do hypothesis tests with a certain level of accuracy, you need to know what the sampling distribution is. So here are three possible ways that you can approximate the sampling distribution of T. Number one, this uses a lot of 882, 883 stuff. Assume a probability distribution for the population. In other words, say Y is distributed something. So you can say Y1, Y2 down to Yn are IID random variables with a distribution F, just to be general. Then using some mathematics, you could find the distribution of the statistic T. How about we call this distribution G? We'll use G a lot to mean the distribution of T. Where do I get this notation? It's from the book. So if you don't like it, blame the book, not me. So T has a distribution G. Okay? You did a lot of this kind of stuff in 882, 883. The problem, though, is how often can one absolutely be sure that Y1 through Yn are IID distributed with a distribution F? Good luck. It's probably not going to happen. That's why this is an approximate way to go about doing this. Part B. Well, maybe with your advanced probability course, if you've taken this, you've seen this way already. All of you should have seen a little bit of this in Cassell and Berger in your 882 or 883. At least it's in that book, and I thought it's been taught before. What you could do is find the asymptotic distribution for the statistic. So, for example, you can say something like this. The square root of n times t minus theta converges in distribution to a random variable x where x has a particular distribution, maybe normal, maybe Gumbel, for example. That appears sometimes in asymptotics. How many of you have not seen this converges in distribution notation? Everyone's seen it? Okay, I will assume then everyone has seen it. Is this taught in 882, 883? Briefly, yeah, that's what I thought. Okay. So, from Kinsella and Berger, and your Kinsella and Berger book will be useful in this course. Hopefully you didn't return it. Now I was outside at the bookstore the other day just to see, what books were there in our department and stuff. And I was on East Campus and they didn't have my book there. I was quite disappointed. But they did have the Kinsella and Berger book, and I believe new. It's like $250. Does that sound right? Yeah, not good. I mean, these book publishers, things are changing in the publishing world, and I think they're trying to get as much money as they can before that change happens. So, from Kinsella and Berger, let's say I have some kind of random variable that is a function of n. So this could be like a statistic like t that is a function of, that t is the sample mean. Obviously, that's a function of n. What that says is, if you want to say xn converges in distribution to x, in other words, as n gets big, this random variable ends up having this random variable's distribution. What that basically means is this, that the limit as n goes to infinity, that the CDF, as a function of n, is equal to some other kind of CDF. So, for example, central limit theorem, all of you have this from 882 or 883. Central limit theorem works like this. Square root of n times t, this is the sample mean, minus theta, if that's the expected value of, let's say, y, converges in distribution to a random variable x, where x is distributed normal 0 sigma squared. Now, sometimes you also see some little bit of abuse in notation just because it's easier. Instead of saying x here, some people might actually put the distribution itself. I'm not that picky. You can use that if you want to, if it comes up. But often you see that. Okay. So what's the problem? So this leads to an approximation. The problem, though, is how often does one take a sample size of infinity? So if I ask you to go take a sample size of infinity, you're going to be out there for a long time. You're never going to reach it. So you have the distribution for the statistic for the one sample size that can never be obtained. That's not good. Well, what happens then at a fixed sample size of n? Well, is it, like in central limit theorem, is it exactly normal? Probably not going to be exactly. Hopefully you took your n high enough that it's approximately normal. And what do we do about the value of sigma squared there? That's a population parameter. What do we do? So that's a problem. So we talked about two ways that you can get this important sampling distribution for t. Here's a third way. Use the bootstrap. So that's what the bootstrap allows us to do. Approximate the sampling distribution for t, and then use that for statistical inference. The bootstrap is, in actual implementation, is really based upon computing power. To actually prove that the bootstrap works, that's where there's some high-level mathematics that comes in. Okay. So, one reason why this is a PhD level course too is that all of you in your, for those of you who are going on for a PhD in statistics, all of you will come to a point where you're going to need to know what's the distribution of a particular statistic. That's what research is about, statistical research. Statistical research isn't, let's say, well, I'm going to apply this analysis to this data set. That's not statistical research. Statistical research that's published in statistical journals is based upon, let's say, driving a distribution for a statistic. I'm sorry, let me say that again. Okay. let me rephrase it this way. So much of statistical research is based upon knowing what the distribution is for a particular statistic. Before you came into this class, all of you had that background, so you could do this. Some of you had the advanced probability course, so you've had two ways to do this. So the reason why you take a Bootstrap course is so that you add to, let's say, your statistical toolbox about how to solve problems. You have now the Bootstrap way to come up with this distribution for the statistic. So if you look at pretty much any statistical paper out there, they're going to present a statistic. They're going to present a way to approximate its distribution. They are then going to evaluate that approximation. Pick up a JASA, pick up a biometrics, pick up a biometrical biometrica, pick up annals of statistics. That's what they do. That's what statistical research is, and that's what you do for a dissertation. Okay. So that's why it's good to have a course on the Bootstrap. Let's see. So, page 6, please. So here's a real short introduction to the Bootstrap to let you know what is the Bootstrap. Did any of you by chance talk about the Bootstrap at all in 883? You did? Not much. Okay. Did you actually do any homework problems on it, or gotten that extensive? Okay, good. So at least some of you know a little bit about what the Bootstrap is. But if you would like an introduction to it outside of our course itself, here are 3 papers on it that are quite introductory. This second paper here by Johnson, he's actually a professor up at South Dakota like School of the Mines, I think. It's based in Rapid City. And this is in the journal called Teaching Statistics. It's a very good journal because I don't know, I like it because I get ideas from it, but it's basically on teaching statistics to like Stat 218, our introductory stat course, and ideas of how to do that. And he wrote a paper on, well, how could you teach the Bootstrap to 218 students? So, it's written at a level that anybody in this room definitely could understand. This next paper is in the journal Statistical Science. This is kind of a journal that's based upon reviews of particular items. So it's not necessarily presenting new research, but reviews. And this is a nice little introduction to it, that with a master's degree in statistics, or pursuing a master's degree in statistics, you should be able to get something out of. Here's another paper by Bill Duckworth and Dr. Bob. That's, Stevenson there. You call him Dr. Bob. He's a professor at Iowa State. And this is a little thing that they wrote up in a proceedings paper for the joint statistical meetings about how you can teach statistics to introductory stat students. I'm sorry, how to teach Bootstrap to introductory stat students. So those are some places that you could start to learn more about this, in addition to my own presentation. But let's talk about this now for my introduction. So we saw how, let me go back, let me actually do a split screen here. I apologize for flipping back and forth. So let me get this on the split screen. So this first way to approximate the sampling distribution for statistic really relied on knowing what F was, the actual distribution of the Y's. Once you know F, you can do some nice mathematics to derive G, the distribution of T. Okay? Suppose you knew what F was, but you actually didn't want to go through the process of all the math. Maybe you're being a little lazy. You don't want to do all that mathematics. How could you use Monte Carlo simulation then to approximate the distribution of T? It's not a rhetorical question. So you know what F is. So you know Y is maybe distributed normal. And let's say you have a sample, you're interested for a sample size of 10. How could you use Monte Carlo simulation then to simulate the distribution for t? Exactly. So what you would do, let me jump over here to Windows Journal. There we go. So what you could do is this. Let's say take R samples of size, this is capital R. You'll see why I'm using the word letter R, not because I'm using the software package R. You'll see why I'm using the letter R coming up. It's notation from the book. Take capital R samples of size n from whatever f is. So you get sample 1, size maybe 10. Sample 2, size 10. Sample 3, size 10. And then, for each sample, calculate t. How about if I call it t sub r? So for little r equal 1 to capital R. And then simply summarize. So one way to visually see the distribution would be to do a histogram. So we have, let's say, t sub r here. You have, say, frequency here. And perhaps, since we like to draw histograms often like this, you get this nice little symmetric histogram. And that gives you a visualization then of the distribution of t. Okay? So that's how you could use Monte Carlo simulation. The problem with that approach is, again, generally you're not going to know what f is. So if we don't know something in statistics, what do we often do? Take a sample and estimate it. So is there a way then that we could get, let's say, f hat? So the estimated CDF. Well, actually, yeah, there is. There is a way that we can do that. If you're using just one sample. In some of my stuff that's coming up here, maybe I want to evaluate my CDF at a particular value of y. So like with the GPA example, maybe I want to know capital F of y. I'm sorry, capital F of, let's say, 3. Of course, that would mean the probability that y is less than or equal to 3. Well, other times I might be interested in this, capital F hat of 3. Well, that would be then the estimated probability that y is less than or equal to 3. So if I have f hat, could we do the same type of Monte Carlo simulation that we just talked about here to approximate the distribution for t? Yeah, just do that. The key is you need to have a way to draw a sample then from f hat. We'll discuss how to do that probably next time. But before we talk about that, let me see where we are here. Yeah, we'll keep on going. So what should we use for f hat? Well, if we wanted to be completely non-parametric, and I like to be completely non-parametric because I don't like assumptions, what we can do is use something called the empirical distribution function, or EDF. The EDF estimates a CDF in a non-parametric way. Anybody heard of an EDF before? What class? Okay. Yeah, I might have done that too. So yeah, I did. So what the EDF is actually a very simple thing. All it is what you will learn like in Stat 218, a cumulative relative frequency distribution. That's it. So in other words, f hat of y, so f hat evaluated at y, is simply the proportion of observations in your sample that fall less than or equal to y. If we want to put it in a little bit more in an equation form, let's look at it this way. Let's say I have a sample y1 to yn, and f hat of y is just simply the number of these y sub j's. And these y sub j's come up from up there. They're less or equal to, let's say, like 3, or 4, or 3.5, whatever your value of y is that you're evaluating the EDF at, divided by your total sample size. A little bit more of a mathematical context, then we could use the indicator function. We could say 1 over n times the sum from j to 1n of the indicator y sub j is less or equal to 1. Where the indicator function, of course, is a 1 when what's inside the parentheses is true, 0 when it's not true. And you could actually write out then, if you really wanted to, write it out for all n terms. Notice how we're kind of assigning a weight of 1 over n to each of these y's. It's going to be important coming up. So what does an EDF look like then graphically? Well, what we could do is this. Excuse me. Let's say that I had this sample here. I don't give you the whole sample because it's not really important. But let's say y1 ended up being 1.54. y2 ended up being 1.8 and so on. And just to make things easy, I've actually ordered everything there. Okay? Sample size of 20. And this is what the EDF looks like. So we have values of y on the x-axis. We have values of f hat on the y-axis. And remember, the very first value that we got was 1.54. So what this plot is telling us is that f hat, for anything less than 1.54, let's say 1.53, is equal to 0. Then once we hit 1.54, we take a step up. We take a step up, in that step, is equal to 1 over 20, or 0.05. Because now, in my sample, the probability of getting 1.54 or less is 0.05. Then the next value in my ordered sample was 1.8. And that's where the next step up comes. Now, I'm at 2 over 20, or 1/10, or 0.1. So what we have here is that, again, for every value in my sample, I take a step up. It's a weight of 1 over n. Notice the very top value here is 1. So let's say f of, I don't know, let's say that this is 3.5 here. F of 3.5, I should say f hat of 3.5, is 1. Just to emphasize the point one more time, let's say I wanted f hat of 1.6. What would that be? Excuse me? Yeah, 0.05, 1 over 20. Okay? So that's my CDF. And in fact, you could look at, let's say, I'm sorry, that's my EDF, excuse me. You could look at the inverse function of EDF. Let's say I want the 0.05 quantile from this EDF. Well, it's 1.54. Remember how that sounds something very familiar to, let's say you want the 0.05 quantile from a standard normal. Well, what you would do in that case is use, let's say, Q norm, P equal 0.05, and you get negative 1.65. So this is just, a different way you can say of looking at stuff. Now we're using the EDF versus a record old parametric distribution to do this kind of stuff. So if I replace f with f hat, you might be wondering, well, is f hat really a good estimate of f? Yeah, it can be. For example, in an asymptotics course, you will learn about this. That the square root of n of f hat evaluated at y minus the true CDF evaluated at y converges in distribution to a normal random variable. But look at that. Look at that 0 there. So what that means is It's called asymptotically unbiased. And here's the variance. I know we're a little bit running out of time here, so let me just briefly mention that if any of you have seen the large sample distribution for a estimated proportion, that's where this comes from. Because all this is an estimated proportion. But we could even go farther. Things are even better in terms of F hat. And in fact, if you've taken Stat 980, this should look familiar, with probability 1, F hat of Y actually converges more strongly than necessarily just that distribution thing that we saw above. Converges with probability of 1 to F of Y. And in fact, you can even use the Glavino-Cantelli theorem, which basically says that the probability that the maximum difference between F hat of Y and Fy, that maximum difference goes to 0. The probability of that happening is 1. In other words, these two are very close to each other as n goes to infinity. So indeed, yes, F hat can be a very good estimate of F. So, now that we have that established, how do we take a sample from F hat? We'll talk about that next time. Are there any questions? Okay, that's it for today.